Okay. So we have said that the operating system is executing actually in the CPU whenever some event occurs. So this event can be a hardware interrupt or a software interrupt, a trap, which will be the result of, for example, a request from the application to the operating system to do something, to get a service, like doing I/O, or if the application is running and trying to do something illegal, trying to access, for example, an illegal memory address, or trying to divide by 0 and so on, then the hardware can detect that and stop the application and give the control to the operating system, which means start executing operating system code, okay? That means we will have a special OS routine to be executed in the CPU to handle that interrupt, okay? So what happens when the interrupt is handled, or while the interrupt is handled? So the operating system, after suspending the currently running application, it preserves the state of the CPU by storing the registers and the program counter related to that application that is suspended to the memory. Okay? So the application was running in the CPU. Okay? The application was running in the CPU. Interrupt arrives, so the application has to be suspended. But the application was using these registers. It had a program counter and so on. Since the application will be run later on again, we save this state, CPU state, we say to that. We save that state to the memory and then run in the CPU the operating system code, the function, handlers, and so on, so that they can overwrite those values here. And then when we are finished handling the interrupt, we reload the application state, the CPU state regarding that application in the CPU, and therefore the program counter will have the same old value. It will continue. It will be able to continue from there. So in this way, the application will be able to run in the CPU as if nothing has happened. Okay? So interrupts and handling them, running OS code from time to time in the CPU, will not affect the correctness of the application. Okay? Of course, it will slow down the running of the application, but it will not affect the correctness of the application. Okay? So the system, the hardware should determine, for example, when an interrupt happens, okay, when interrupt arrives to the CPU, the system should determine what type of interrupt it is and so on. It will obtain the interrupt number, and then it will use that number, for example, as an index to an interrupt table, interrupt vector, to find out the address of the interrupt service routine to be run in the CPU. Okay? So we have several different functions, separate segments of code in the kernel. All right? That determines actually what action should be taken whenever an interrupt happens. Okay? So for each type of interrupt, we have a separate OS routine interrupt handler to be run in the CPU. Okay? So whenever a keyboard interrupt arrives, for example, we run this routine. Whenever a disk interrupt arrives, we run that routine, which is part of the kernel, part of the operating system. Okay? So they are not the same routines. Okay? So the others of those routines are found where? In the interrupt vector. Okay? So this is the interrupt processing timeline. So when the CPU, for example, is running an application, that application may request some I/O from the system, okay, to be done. Then the I/O device may start doing the I/O. It may start doing the I/O. So since the I/O device, I/O controller, the device controller and the device itself may do the I/O in parallel with the execution of the CPU, while the CPU is executing the application code, the program code, the device may do the I/O with the device. The device controller may do the I/O with the device itself. For example, the device controller, disk controller can do the I/O with the disk, okay? And assume at this time the I/O is finished. The data is available from disk in the disk controller. So then what happens? The disk controller interrupts the CPU, indicating that now read operation is completed from the device to the controller. So that causes the CPU to stop the currently running application. So it's no longer running in the CPU, but interrupt service routine, disk interrupt read service routine is running now in the CPU to handle that interrupt. Okay? Handling that interrupt may mean, for example, copying the data from here to the memory, from the device controller to the memory, or initiating that copy operation with the DMA and so on. Okay? After you handle that interrupt, meaning that initiate the copy operation from the device controller to the memory, or copy the data from the device controller to the memory by yourself. That may be done by the interrupt handler and so on. So when it has finished, again, the CPU is running what? It is running the application that is suspended, okay? So from time to time, the CPU is running interrupt handlers or kernel code, and then in the rest of the time, it is running the application code, the program code, okay? The programs that we are running every day and that we are developing with Java, C++, and compiling and running, okay? Any questions so far? Okay, so the applications, as I said, cannot touch to the I/O devices directly. Okay, the program that you are writing. Okay, you don't want to deal, for example, when writing a C++ program, you don't want to deal with the details of the hardware. You just want to call a function to do I/O, to get something from the keyboard, to write something to the screen. You just would like to call a function, right? You do that. You call, for example, printf, scanf, and so on, to write something to the screen or read something from the keyboard, okay? But actually there is no magic. So how is actually that data that you would like to write to the screen is actually going to the screen controller, okay, graphics card, and finally to the screen? Somebody is actually putting the data in your variable, getting the data from your variable and putting it into the graphics card. Who is doing that? The operating system, right? So what you are doing is you are just calling an I/O function here, which is finally triggering some operating system routine to move the data to be written to the screen to the respective device controller from where it is put to the device. This can be the screen, for example, okay? So basically the applications, while doing I/O, they request services from the operating system, okay? This is called calling system calls. The services that OS provides to the applications that can be called by the applications are called system calls, okay? So the applications may trigger the execution of those system call routines, operating system kernel routines. Then they are executed in CPU. They can further call the device driver routines to talk to the device driver, to talk to the device controller, and finally the controller, when it has the data, it knows how to put the data, for example, to the device or get the data from the device and so on. So the system call routine in operating system performs the I/O via the help of the device driver routines in the operating system. Okay. So the OS, while doing that, can maintain device status table, one entry per device. The entry for a device, for example, may keep whether the device is busy and so on. It may keep the state of the device and so on. After issuing a system call, okay, after calling a kernel routine to get a service, like to get an I/O done, an application may wait for the call to finish, which is called blocking call, or may continue to do something else in the CPU, which is called a non-blocking code, okay? So in order to speed up the movement of data from the device controller to the main memory, we know that we have a hardware support called direct memory access, okay? So that actually enables the CPU not to take part in the movement of the available data in the device controller to the main memory. Without DMA, the CPU itself copies the data from the device controller to the main memory for a read operation from a device, for example. If the application would like to get something from a device, from the keyboard, disk, and so on, the application will call the system call, the respective system call. Finally, that respective system call will trigger some routines in the kernel to take the data, available data from the device controller and move it to the main memory. Okay. But if the CPU is involved in that operation, the data here can be quite long, and during this time CPU cannot do useful tasks. It will not be able to run application code. If we have DMA support, then the DMA helps in moving the data from here to there, okay, without CPU's intervention. In this way, CPU can do something else during this time, can run some useful application code, okay? So DMA speeds up the things, okay, and also relieves the CPU from those copy operations. So in summary, the computer operates like this, okay? We have the CPU doing the processing, memory doing the storage, and we have the devices doing non-volatile storage and doing input IO, input output and so on, keyboard, disk and so on, right? So when you would like to run a program, what happens? You load the program into memory. Before that, when you power on your computer, what is loaded first? The kernel, the operating system code is already loaded into memory, okay? It's always there in the memory. But when you run a program, if you want to run a program, the program is loaded from the hard disk first into the memory. So what's a program? It's a sequence of instructions plus some variables, data, we call that, okay? Arrays that you define, integer variables and so on. That is the data portion of the program. So then the program starts executing. What it means is the CPU takes the instructions one by one, okay, and executes. The sequence of such instruction execution is called a thread, okay, a thread of execution. So while the instruction may execute, for example, maybe an arithmetic instruction, then the CPU is doing the job. But sometimes if you would like to do I/O, then what do we do? Then we make a I/O request to the device with the help of the operating system. You call a system call, a routine of the operating system to initiate the I/O. During this time, the operating system routine is running in the CPU to initiate the I/O to the device. It talks to the I/O controller to initiate the I/O operation. And while the I/O is actually performed, the CPU can run something else. And when I/O is finished, the device interrupts, okay, the CPU so that the CPU can get the data from here and move it to there and make the data available to the application. Okay, moving it there to here means that you have the data now available in your variable. Okay, so you, for example, do a scanf in the C programming language, okay, and you give the address of a variable there in the scanf as a parameter. So what happens? During this time, your program is blocked, is waited until scanf actually gets the value from the keyboard and puts that into the variable. So this is the device keyboard. When the user presses to the keys, okay, the data integer value will be available here, and this will generate an interrupt, and CPU will take that and will put it into your variable here, and now the data will be available in your variable, okay, the integer will be available in your time, and then your application, your program will be able to continue with the next statement after the scanf, okay? But during this time, it may wait, and the CPU can run another program that is started while your program is waiting, okay? It may not become idle all the time. Any questions? So this refreshes our computer organization knowledge about how a computer is organized, the hardware is organized, and how it operates, okay? So this is how it operates, and while the hardware is operating, it needs some other devices like the storage devices where we store the data. So the main storage element in the computer is the main memory, and it is the only element that is large enough and that is quite large to hold the programs, and also it's directly accessible by the CPU. Okay, the CPU can directly access the memory, all right, but it cannot directly access and address the disk. Okay, so but the main memory cannot hold everything. It cannot hold all the files. Okay, plus the main memory is actually a volatile storage. Okay, you will lose the data when you power off your computer. Therefore, we need some other storage like the hard disk, which is non-volatile, and it's also larger than the main memory, so it can keep lots of things, okay? So therefore we have hard disk and so on that are non-volatile, that are the extension of the main memory. So that we call them, therefore we call them as a secondary storage. So main memory is the primary storage in your computer, but it is volatile. So we extend that, we have a bigger space now in the hard disk, but it is slower, but it is also non-volatile. You will not lose your data. The data will be permanent there in the hard disk, okay? So this is the secondary storage. So this means that we should have several different storage components in a computer. There is no technology at the moment available for memory. So it can give us a memory component that is fast, that is non-volatile, and that is very large. We don't have that technology yet. We have, therefore, several storage elements, hard disks, memory, caches, tapes, CDs, and so on. Together, they make up the storage system in the computer, okay? So therefore, the storage system in a computer is organized into a hierarchy, all right? And the hierarchy consists of different storage elements with different speed, cost, and volatility. For example, we have memory, we have cache, hardware cache, we have hard disk, we have CD, and so on, okay? So each have different values for these parameters. So, and this brings the issue of caching. Even though the data is in a large storage, okay, but the access to that large storage can be slow, but you may want to access to that data very fast. Okay, how can you do that? There is the caching idea. You can copy the data into a faster storage system and access it from there. So usually what we have is, even though the data is large, okay, some pieces of that is accessed much more frequently than the other pieces. Then you can bring those frequently accessed pieces of the data into a faster storage and access it from there. Okay? So this is the caching idea. You copy the information to a faster storage system, and for example, the main memory can be viewed as a last cache for secondary storage. For example, if some disk blocks files are accessed heavily on the disk, okay, you can bring them into main memory. The main memory is smaller compared to the disk, but faster, okay? But it is not very large to hold every file. But the frequently accessed files can be brought into memory and accessed from there. In this way, you reduce your average access speed, okay? Or you increase your average access speed and you reduce your average access delay, okay? So this is the caching idea that is heavily used if you have hierarchy or storage hierarchy. If you would have a single storage element that is very fast, that is very cheap, that is non-volatile, then you would not need that concept. But since we do not have that yet, we have a hierarchy of storage elements, we need the caching idea to speed up the processing. So what is the hierarchy in a typical computer? At the top of the hierarchy we have the registers. But we have a small amount of registers in a computer system, maybe 32 registers, okay? Less than 1 kilobyte in total storage size. Then we have the hardware cache. We have the memory RAM, where the programs are loaded and run, but the frequent accessed parts of a program, instructions or the data, is brought into the cache, right? You know this from the computer organization course. Then we have the magnetic disks. We can have electronic disks in between. The magnetic disks have larger storage than the main memory, but access to them is much slower compared to main memory, okay? And we have the optical disks like CDs and so on, offline media, and magnetic tapes and so on. So these are offline media. The CD is not always available in a computer. You have to put it into the CD drive, then it becomes available. Therefore, we can call it not online all the time. So we have a hierarchy. When we go down in this hierarchy, you actually increase the typical size of the storage element. You also increase the access delay, okay? Speed is reduced, but the cost is also reduced and so on, okay? When you go to the higher levels in the hierarchy, then access speed is very fast, but the cost is also much higher, and the size of the typical storage element is also much smaller, okay? So as we said, the caching idea principle helps us in increasing the speed, okay? It's performed at many levels in a computer, okay? The caching idea can be applied, for example, between a large and slow storage element and small and fast storage element, like main memory and registers, or main memory or hardware cache, or like hard disk and main memory. Main memory can act as a cache to cache the frequently accessed files or blocks. Tape or hard disk. The hard disk, for example, may cache the frequently accessed files from the tape or CD. If a file is accessed once every year, then you don't have to keep in the hard disk. You just can keep it in the tape, right? So the caching idea is a general idea, okay? It is not an idea that's applied at the hardware cache level. But with the caching idea, you have to, of course, decide on several issues, like, for example, what should be the size of the cache, okay? How large should be the cache? And what should be the replacement policy? Because when you cache items here, sooner or later the cache will be filled up. Then you will need to replace some items to bring new items and so on, okay? So these are the issues that has to be solved. All right, so we have talked so far about the general organization of a computer. Now let's look to the processing. So what kind of processor do we have nowadays? Nowadays, we have actually multiprocessor systems. 10 years ago, we had, or PCs were actually running or having only a single CPU. Now, it is very common that a PC has at least 2 CPUs, okay, 2 cores, 4 CPUs, and so on. So we are going towards multiprocessor systems. Most systems use a single general-purpose processors, like PDAs. In the past, mainframes and all PCs were using actually a single general-purpose processor. Okay, but now we have the multiprocessor systems are coming, and are becoming popular and growing in use and importance. So what is the advantage of multiprocessor systems? A multiprocessor system is this: you have a computer, a system, in which you have not a single CPU but multiple CPUs. Okay, multiple processors, but those processors are sharing the same memory. They also share the same hard disk, okay? So you have multiple processors, but a single RAM, okay? So what is the advantage of that? First, increased throughput. That means you can have more work done per unit time in such a system. You can run one application in this CPU, another application in that CPU, and so on. The second advantage is economy of scale. What does it mean is that this configuration is much cheaper than using, for example, multiple computers. By 4 PCs, interconnect them. Okay, this is an environment where you have multiple computers. Each computer has a CPU. That means that environment will have 4 CPUs. But that will be more expensive. Here you have a single computer with 4 CPUs. That solution will be cheaper. Okay, economy of scale. And the third benefit is increased reliability. If one CPU fails, without the user being aware of that, the applications can be started running in other CPU, okay? Therefore, the computer may continue operating, okay? So therefore, you have increased reliability in the system. There are 2 types of multiprocessing. One is asymmetric and the other is symmetric. In asymmetric multiprocessing, what we have is we have a processor acting as the master, and the other processors are slaves, and the master controls which slave is actually running what, okay? In the symmetric multiprocessing, we do not have such a we don't have such different roles for the processors. Every processor has the same role. Therefore, it is symmetric, okay? They have the same responsibility and they have the same role. So the symmetric multiprocessing is actually common. In symmetric multiprocessing, what we have in the same computer, we have different CPUs, okay, each having the same capability, being able to run programs. And the operating system, for example, decides which program to be loaded and which programs that are loaded into memory will be run in which CPU. It may decide, the OS, system software can decide, this program will be run here because that CPU is idle and so on, okay? So therefore, the CPUs, there is no special CPU here that is acting as the master, as in asymmetric processing. But in symmetric multiprocessing systems, all the CPUs have equal capability and role, and the system, the operating system, decides which CPU will be running which task and so on, okay? So this is the common architecture in your PCs that are dual core, okay, where you have at least 2 processors, okay? This is the architecture. Symmetric, they are doing symmetric multiprocessing, okay? They have several CPUs that are sharing the same main memory. The main memory is shared, okay? Each CPU is sharing the same memory. So in a dual core design, which is common nowadays, what we have is we have in a single chip, physical chip, which you can open your computer and see, okay? In that chip, you will have multiple CPUs implemented, okay, in the hardware. So we say that multiple cores, okay? So in a single chip, for example, this is maybe the chip, okay? This area may be the chip, a single chip. Inside that, you can have actually 2 CPUs sitting, okay? Each having its own registers, or each having also its own cache. Sometimes the caches may be shared, but each CPU will have its own registers, of course, the processing unit and so on, the control unit and so on, will be there in each CPU. All right, so multiprocessor systems are common, okay, so that in which you have a single system having many CPUs, okay? But what you can have is also, you can have single CPU systems, multiples of them, which will be a more expensive solution, of course. You have multiple systems connected together, okay, implementing a clustered system. So a clustered system is like a multiprocessor system, but multiple systems, computers, are working together to solve a problem, okay, or to satisfy the computing needs of a facility. So they also usually share storage via a network, which we call usually as a storage area network. So we have multiple systems, computer systems. This is a PC, for example, with a single processor or maybe multiple processors. This is another PC with a single or multiple processors, and they are interconnected together with a fast local area network, a storage area network, okay? And some of these PCs may have hard disks that is to be shared by all the members of the cluster, okay? So these are the members of the clusters. So then this is a clustered system, okay? What is the benefit of such a system, having such a system in a facility, in a department, for example, to solve the computing needs? Increased availability. For example, one of these PCs may be always acting or operating in hot standby mode, meaning that it is not running normally applications. But when one of the other PCs fail, the applications that has to be run there will be now running in the PC in hot standby mode. So this comes into picture whenever one of the PCs fail. Okay? So in this phase, you are increasing the reliability, computing reliability in the department. Okay? This is called asymmetric clustering. In symmetric clustering, you have multiple nodes running applications and monitoring each other whether they are still available or not. So all the PCs are running applications, but also they are monitoring each other. So if one of the PCs fail, then this will detect that because it's always monitoring whether it is up and running. Okay? If it detects that, then the applications that are running here can be started here and so on. Okay? So this is called symmetric clustering. Okay? Any questions so far? So we have finished the review of the computer hardware and computer organization, which you have seen in very detail in CS-342 course. So now we will talk about some major operating system and structures and concepts. Any questions that you would like to ask? Okay, so multiprogramming. So nowadays, all the operating systems are usually multiprogramming systems. In the past, we had an operating system being able to run one program at a time. You could not start two applications at the same time. A web browser and an email reader could not be started at the same time in the older systems. Nowadays, you can do that, right? You can start an email reader at the same time. You can start a web browser, another web browser without any problem. You can start 20 applications at the same time, sharing the same hardware. This is possible. This is possible because the operating system supports that. Okay? And this idea is called multiprogramming. So it is good for the user for convenience because now the user can start many applications, and also it is good for the efficiency. Okay? It actually increases the system's efficiency. Why? If you had a single application, which we call job, okay, running in the system, okay, then that application may be using the CPU from time to time, and then waiting for some I/O to be done. If that is executing, for example, instruction like scanf, that is waiting for some I/O to be done with the what? With the keyboard, right? Which may take a few seconds, minutes, and so on, depending on the user. During this time, the job is just waiting for that I/O operation with the keyboard to complete. It is not running in the CPU. Then what you do with the CPU? Nothing. You are wasting the cycles. Okay? So you are not utilizing the CPU during this time. If you have a single job available, loaded in the computer. Okay? But if you have multiple jobs available in the RAM, what will happen? If you have multiple jobs available here, what will happen? If one of the jobs is waiting for some I/O device, the probability of another job is also waiting for I/O will be reduced. If you have more jobs, that probability will be reduced more. Okay? So if you have several jobs, then the probability of all of them is doing I/O, hence waiting, not running, is quite low. So that means at least one of them can run in the CPU. Then what is the benefit? That means you are actually utilizing the CPU better. You are obtaining more efficiency. You are using the resource available in the computer more efficiently in such a system. If you look to a time interval, you can have much more jobs or tasks done, okay, compared to a system which executes the jobs in sequence. Okay, execute one job, and it finishes, execute another job, and so on. In a system which is doing multiprogramming, you will have better utilization and better throughput. So multiprogramming organizes jobs, the programs, code and data into memory so that CPU always has one job to execute it. Alright? So a subset of total jobs that is to be run in system is kept in memory. So several programs has to be loaded for that to become a reality, okay? Several programs have to be loaded into main memory and be ready to execute in the CPU. Alright? So you have to partition the memory in such a way. So memory management is required, of course, for multiprogramming and so on. So this is one important idea that operating systems has to implement, okay? Multiprogramming. An extension of this idea is the time sharing, okay? Or which is called multitasking. So it's a logical extension. Again, you multiprogram, you actually bring several programs into the CPU, but now you bring several programs into the memory, and you share the CPU among those programs. You share the CPU among those programs as here, but you share it so frequently, meaning that you actually switch the programs to use the CPU so frequently that users can interact with each program or job or process that is running while it is running, creating interactive programming. Okay? That means that if those jobs or processor applications are interactive, require user interaction, okay? So that means the CPU's response to that should be quite fast. So when this job is waiting for some I/O to be done with the user, okay? When the user gives the input and hits the return key, okay? Then this becomes runnable. So the time for the next execution of this job should be quite fast in order the user to see some immediate output computation, okay? So therefore, the CPU should switch among those jobs so frequently that the user does not wait until the next execution of the job, okay? So for example, every 100 milliseconds, the CPU switches between jobs. For 100 milliseconds, it executes this job. For another 100 milliseconds, it executes that job. For another 100 milliseconds, it executes that job, and so on. This is quite fast switch, okay? In this way, a user waits at most 300 milliseconds to get a response, okay? But if it would wait 30 minutes to get a response, meaning that the CPU is running this 10 minutes, and 10 minutes, 10 minutes, this is also multiprogramming, but the response time will be very low, very long, okay? This is not tolerable for interactive applications. So multiprogramming is good, and it's enough for non-interactive applications, but you have to have time sharing support and multitasking support in the operating as well, which requires the CPU to switch between programs so fast so that those programs now can be interactive programs, okay? And the user will have a low, small response time. So the response time usually should be less than 1 second in order that system be acceptable for the user. Otherwise, the user will not wait for 1 or 2 minutes to get a response. Every time you hit the return key to get a computation done after you give the integers, okay? If you wait 1 minute, then you will not like that system, right? But if the response time of the system is less than 1 second, then it is a good system, right? That means, in the worst case, the order of execution will come to your, the turn of execution will come to your program in less than 1 second. No matter how many programs are running in the system, maybe 10 or 100 different programs will be loaded into memory and running concurrently. So this is the time sharing idea, okay? It's a major idea that is implemented also by the operating system. And another major idea is virtual memory idea, which extends the physical memory, okay, so that you can run programs that are larger than the physical memory. Okay, you will see what virtual memory is later on. And while switching, for example, among the jobs to implement multitasking or time sharing, the CPU has to decide which job or process to run next. And this is called CPU scheduling, okay? So there are different algorithms for that with different properties. We will see that also in another chapter. So then this can be the memory layout of a system that implements multi-programming and multitasking. So instead of the operating system is always in the memory, so this is the memory layout, okay? So OS is always in memory when it is loaded at system boot time, right? When you power on your computer, it's loaded and it will be in memory until you power off your computer. It's always there. But in a single task system, you will have only one job load and running. But in a multitasking environment, multi-programming environment, you will have lots of jobs loaded in the memory, start the execution, okay? And those jobs are sharing the CPU. For some time, this job is using the CPU, and then that job is using, and so on, and later on, again, this job is using the CPU. They are time sharing the CPU. You have a single CPU, or 2 or 4 at most, but you can have 100 jobs sharing those resources, okay? And we have a single RAM, again, shared by the many processors. Here, this memory is shared by the processor so that each a different portion is given to each different process. Okay, so they are actually this is space multiplexing, right? You are sharing space. In the CPU, you have a single CPU which is used for some time by one process and another time by another process. Okay, so you are actually now doing time multiplexing. This code you are actually sharing. This is called time sharing. Okay, so for the memory you are sharing space. For the CPU, you are sharing time, okay? To implement multiprogramming. As I said, the operating system operates in an interrupt-driven manner by hardware and by software running. A software error in the application running may cause the OS to come into picture and execute the CPU, okay? Or the software running, the application running in the CPU may call a system call, may request a service from the operating system, this is called trap. That will cause, for example, also some OS routine to run in the CPU to implement and do the service, okay? Other process problems may include, may be there, which is handled by the system. For example, an important feature that the system should have is the processes, the applications that are running concurrently should not modify each other, should not interfere with each other. So this is the protection, okay? And also they should not modify the operating system, okay? And access to the resource should be controlled. I/O devices should be touched only by the operating system, not by the applications. In this way, while I am printing something, another user may not print because it is under the control of the operating system, right? So this is handled by a dual mode operation. Also, sometimes a program that is implemented wrong, okay, may have an infinite loop. When that program starts running in the CPU, it wants to run infinitely, okay? But the system should not allow that. And this is handled by use of a timer interrupt. So let's look to these issues now a little bit more. What is the dual mode operation and what does it have? So dual mode operation allows the operating system to protect itself, the I/O devices, and other system components. So what is dual mode? Dual mode is actually requires hardware support. So dual mode means that the system is actually operating in two modes, user mode and kernel mode. When it is in user mode, that means it is running application code in CPU. When it is running in kernel mode, that is, it is running kernel code, operating system code in the CPU, okay? So what hardware provides is, it has actually a mode bit. It's one bit in one of the registers in the CPU, okay? Mode bit can be 0 or 1. If it is 0, for example, it may mean that the hardware is now running in kernel mode. If it is 1, it may mean that it is running in user mode. So with that mode bit, what it provides is, it provides the ability to distinguish when the system is running user code and kernel code. And the hardware is designed in such a way that some instructions available in the instruction set of the architecture are privileged, okay? And they are only executable in the CPU if the mode bit of the CPU is 0, kernel mode. Otherwise, they cannot execute. The CPU will deny executing those privileged instructions if the mode bit is not 0, kernel mode, okay? So therefore, the instructions of the computer architecture is divided into normal instructions and privileged instructions. Normal instructions can be run by the application programs, but privileged instructions cannot run. But all the instructions can be run by the operating system code. Okay? When operating system is running, all the instructions should be able to be executed. So when the hardware is in kernel mode, any instruction can be run, whether privileged or non-privileged. Okay? So, but when the hardware is running in user mode, only normal instructions, non-privileged instructions can be run. What are the privileged instructions? For example, an instruction that is writing some value to one of the device controller registers is a privileged instruction. Okay? Because that means it is actually doing I/O or issuing some I/O command to the I/O controller. This cannot be done by the application code. So such an instruction should not be run in user mode. It should be run only in kernel mode, during which the operating system routines will run. Therefore, what we should do is that when the operating system should be run in the CPU, we should change the mode bit to which mode? Kernel mode. And when operating system has finished running in the CPU and now application code will run in the CPU, just at the time we should change the mode bit of the hardware to again user mode. Okay? So that the application will not be able to run privileged instructions. Okay? So then we have such a timeline for the execution and transition from user to kernel mode and so on. So assume the user process is now executing in the CPU and it makes a system call. It calls an operating system routine to get a service done. So the OS routine will run. While doing that system call, switching to OS routine and running it to the CPU, just at the time, this is done by actually executing a special instruction in the CPU, machine instruction, which is called usually trap, okay? That is actually setting the mode bit to 0, setting the mode bit to kernel mode. While this process was executing, the mode bit was what? User mode, right? When system call is to be executed, or is to be executed, then the mode bit is set to 0, so that now the mode bit of the hardware indicates that it is kernel mode, okay? So then operating system routine or is executed, which is the system call executed to do the service required, maybe I/O service, okay? So during this time, the OS routine is running, kernel routine is running, kernel is running in the CPU. When it finishes running, okay, then what will happen? The control CPU will be given to the application program. So just at the time, while returning from that function of the kernel, mode bit again will be set to 1, to user mode, and then application code will be run. Okay? So from setting user to kernel mode, anybody can do that. Application program can do that. But from kernel mode to user mode, only the kernel can do that. Okay? All right. Any questions? Sorry. The application that is running, okay, it has to execute from setting to kernel mode, okay, a special instruction, trap, causes the mode bit to be changed from user mode to kernel mode, okay? And after you execute the trap instruction in your program, you can no longer continue running. Definitely, system executes operating system call, okay? Any questions here? So with this mechanism, actually, we can protect the system. Okay, privileged instructions can be run only in kernel mode and not in user mode. Therefore, the OS routines that are executing privileged instructions can do whatever required in the system. Can touch to the I/O devices, can do whatever required. They can write into any memory location and so on. We rely on the operating system and we rely on that. Okay, we assume that it is working correctly. But user programs cannot do anything they want. Cannot execute any machine instructions they want, okay? They cannot execute privileged instructions. Any questions here? Okay. Another issue was, how can we prevent a process, for example, running in the CPU for an extended amount of time or for infinite amount of time? So there is another mechanism that prevents that, the timer mechanism, okay? We have the timer device to prevent infinite loop, a process running in the CPU forever, hogging the resources. So how can we do that? the operating system, for example, sets the timer device to interrupt after a while. Timer device can be programmed in such a way that after some certain amount of time, let's say 100 milliseconds later, it will generate an hardware interrupt. The operating system can do that. Okay? So that interval can be a fixed or variable interval. So then, after you set the timer, the operating system sets the timer during this time, it's executing the CPU. After you set it, what you do? You give the control of the CPU to an application program. Okay? Application, for example, gets executed now in the CPU. Okay? Assume it's an application that will loop immediately infinitely. Okay? So the application is now running in the CPU. The CPU accesses the program. Do you think that that program will be able to run in the CPU forever? No. After 100 milliseconds later, the timer device will send an interrupt. And the hardware mechanism definitely ensures that whenever an interrupt happens, the currently running application is suspended. This is dictated by the hardware. Okay? And the operating system handler is run. So now that means you give the chance to the operating system at this time to run the CPU in the CPU. Okay? So CPU starts executing timer handler of the operating system, a routine of the operating system, a function of the operating system. So in this way, OS gains the control of the CPU. So OS can do whatever it would like to do. It can schedule, for example, the same process to the CPU so that the same process can continue looping in the CPU, or it may decide to run another process. Okay? Then OS sets the timer again, of course, after starting the same process or another process, before starting the same process or another process in the CPU. Okay? OS should set the timer again, so that the timer will again interrupt after a while, maybe 100 milliseconds later again. Okay? And with this mechanism, we prevent a process running in the CPU for an infinite amount of time. Okay? Okay. So we have some other topics to cover in this introductory lecture, but we are finished for time. So on next Thursday, we will cover the basic functions and components that an operating system has, right?